What is up, you guys? Welcome to the 21st lecture of this course entitled Convex Optimization. In this one, we will be talking about weak alternatives. That is, let's say you're in a case where you've got a system of inequalities and equalities, hereby denoted by S, and your main question is simply, is S feasible or not? That is, where my Fi's should all be non-positive and my HI's should all be 0. This is a very important question to answer in optimization theory. So, and this one will not be restricting my Fi's to be convex or my HI's to be affine. So weak alternatives apply to optimization in general. So to answer this question, that is S feasible or not, we're going to take a look at another question, at another dual question, if you will. We're going to try to answer this question using another set of inequalities with no equalities that are lambdas and my dual function g. It turns out that using, and that's what weak alternatives say, is that at most one of the two sets, the first one being S, the set that I'm interested in, and the second one being T, another set that might help me in answering my question. It turns out that at most one of the two is feasible, and it happens as such. So if T is feasible, then S could not be feasible, and vice versa. If S is feasible, then T couldn't be feasible. This may turn out to be useful when working with inequality constraints that are numerically hard to compute. You might want to first take a look at the dual set T, which we call T in this lecture. So T, this set over here, or this set over here, and S is this set over here, or likewise this set over here. It might turn out that T could be numerically easy to work with. That is, G looks nice. It could be easily, plotted on any software you want without having to wait too much time to compute G. And you could pause and take a look at G and say, can I find a lambda in U that enforce G to be positive where my lambdas are positive? If yes, if you could, then you could stop looking in S and you could be assured, you can say, oh, I am 100% sure that S is infeasible. Actually, taking a look at or numerically writing down algorithms to, compute Fi and HI's is going to be useless. So you could pretty much save a lot of time without having to, address or try to do a brute force search on S to see if it's feasible or not. And likewise, let's say you have another problem. Let's say you have problem 2 where, you're looking in set T, that is lambda positive and G lambda nu also positive. And your question is T feasible or not? Well, it might turn out to be that S is easier to compute, and using the same discussion that we held in the first statement, you could look for X that satisfies these constraints, and if you could find one X that satisfies S, then you could be 100% sure that T is infeasible. That is, there is no Lagrangian pairs lambda and nu that satisfy T. In this lecture, we'll be walking through the steps on why am I allowed to, or what connects S with T, okay? So without further ado, let's get started. So in many problems in convex optimization or optimization in general, the objective is not only to solve the problem, but, to look at it before, to check whether it is, feasible or not. And that's what the theorems of alternatives seek to do. So let's start by a system of inequalities and equalities, right? Because that's what, most or all constraints of optimization problems include. So let's say I've got the following system of inequalities that are Fi of x negative, right? Where my I goes from 1 down till m, let's say. So this is my set of inequalities, and I've got a system of equalities that are hi of x equal to 0 for I going from 1 down till p, right? And the question is this system feasible? So this is what we will be interested in, right? It turns out that, we could answer this question by taking a look at the dual function, okay? So for this, we need a certain optimization problem, right? So why not define a problem where, we're minimizing, let's say, 0 subject to the following constraints that I'm looking towards knowing if it's feasible or not, right? So it turns out that if we take a closer look at this problem, right, we're minimizing 0, right? We're not doing anything fancy. So this problem has an optimal value, p star, that is defined as 0 if this set of, inequalities and equalities, let's call them, I don't know, what do you want to call them? Let's denote it as set S. So p star is 0 if S is feasible, right? Because if it's feasible, then, any x would do. So pick one x that is feasible, then you minimize your cost. That is already 0, so p star is 0. Otherwise, it is infinity since we don't have any x that satisfies S. So infinity if S is infeasible, right? So determining whether S is feasible or not depends on the optimal value of this problem that we formed. So you grab your system of inequalities and equalities that you want to, find if they're feasible or not. You form a minimization problem putting S as constraints. You minimize 0, and then there you go. P star would tell you if S is feasible or not. Okay? Now, stopping here is foolish because you didn't do anything fancy, right? You just created a useless problem, but I don't know. You're minimizing 0, you put your S as constraints, and then you're just rewriting your problem in a different way by this optimization problem. So we didn't do anything fancy over here. It could be of interest then to look at the dual function. So the dual function, that is g lambda nu, where lambdas are attached to my inequality constraints, nu are attached to my equality constraints. Oh, and by the way, before I continue, we didn't do any assumption on fi's and hi's, okay? We're just assuming that their domains are non-empty. We didn't say that fi is convex, hi's are affine, nothing about that, okay? Actually, we'll see this in the next lecture where we'll be dealing with strong alternatives. So with strong alternatives, we impose such a constraint so that the problem is convex, and then we arrive at something called the strong alternatives. But we'll leave that for the next lecture. It is out of the scope of this lecture. So for the moment, just keep in mind that my domains are non-empty. That is, fi, each of the fi's to get at least one of my fi's or hi's has a domain, okay? Keep that in mind. Okay, so if I take a look at the dual function, right? Well, the dual function is the infimum of the Lagrangian function. So it's the infimum of f with respect to x over d, where d is the domain of the problem, of Lx lambda nu, right? So what is my L? It is f0, which is already 0, plus lambda I fi, sum over that. So let me write that down. So it is the sum, I running from 1 till m, lambda I fi, right? Plus a sum, this time over my mu's. So I going from 1 till p, nu I hi of x. Okay, now let's define the dual problem, right? The dual problem is nothing other than maximizing over lambda and nu the dual function g lambda nu subject to positivity on my lambdas, right? This is my dual problem. So remaining consistent with notation, the optimal value of the dual problem is denoted by d star. And let's take a look here at what d star is. Let's try to figure it out. So it's actually pretty easy. It depends if g is positive along with the lambdas. If we can find a lambda and nu in which g is positive, then d star is infinity. Why is that? It's because if g lambda nu is positive, it means there is a lambda i's, nu i's that could yield this thing to be positive, right? So maximizing this would only mean to increase lambda i's as much as possible, right? So that being said, if I can find lambdas that are positive, in other words, a feasible set in my dual problem, given that my g is positive, so if I can find such a pair, so in other words, if this is feasible, then d star could blow up to infinity. Now on the other hand, if this thing is infeasible, then the infimum would be to just 0. Here we just quantified the optimal value of the dual problem in terms of the positivity of g and lambdas. But how does this relate to the initial question, that is S feasible? Or in other words, how does S relate to d star? Well, we can use weak duality. And why weak duality? Is because this problem is not convex, so we can't, ensure strong duality. So when I've got weak duality, that is d star is less than p star, we can actually relate S, the set S, with the dual problem. So we've got two cases over here. If I denote this set by T, then notice the following. So we're trying to see if there's any relation between S and T, right? So we're trying to answer the question, is S feasible, in a different way, using T, using the help of T. So if d star is infinity, then p star has to be infinity, okay? If d star is infinity, that is, T is feasible, this directly implies that p star has to be infinity. It cannot be 0, or else weak duality doesn't hold, and this is not allowed. So p star is infinity. Going back up, it means that S is infeasible, right? Now, this is one case. The other case is when p star is 0. So if p star is 0, that is, going back up, P star is 0, it means that S is feasible, right? Then D star has to be 0. It cannot be infinity, or else weak duality doesn't hold. So D star has to be 0, and thus T is infeasible. So what does this tell us? It tells us that at most one of the two, S or T, is feasible. It cannot happen that both are feasible, because if one is feasible, then the other is infeasible. But it could happen that both are infeasible. We didn't say anything about infeasibility. So if you notice that A yields B in both statements, it always starts by either one is feasible. So it doesn't assert anything about infeasibility. It just tells you that if T is feasible, then S is infeasible. It doesn't tell you what happens if T is infeasible. If T is infeasible, well, S could be infeasible and it could be feasible, right? So we have two cases over here. T is feasible, that is the set lambda positive, this is T, what I'm writing down, and G lambda nu, strictly positive. If this set is feasible, then my initial set S, that is fi of x negative and hi of x equal to 0, is infeasible. So this is the first case. And the second case would be if set T is infeasible, then my set S has to be feasible. Okay? So in other words, those two sets are said to be weak alternatives. This is what we mean by weak alternatives. It means at most one of the set of inequalities and equalities are feasible. So why is this important? Why do we care, right? It turns out that, sometimes before checking if a system of inequalities and equalities hold, it might turn out to be hard to just, try to look rigorously for an X that satisfies both inequality and equality constraints. However, if you take a look at the dual constraints, G lambda nu and lambda positive, it might turn out to be easier. So let's say you're in a situation where you found your G. And by the way, I have a mistake over here. This set should be here and this set should be here. I'm really sorry about that, and I'm going to correct it. Okay, so this is what we should have. Again, I'm sorry about that. Okay, so back to our discussion. If you manage to find your G and lambda and you found a candidate lambda nu such that the set is feasible, then you could be 100% sure that your initial set is infeasible. S is infeasible. Now, on the other hand, let's say you're interested in the set of inequalities T that are lambda positive and G positive. Let's say it's hard to work with this set. It's numerically hard. Computing points of G is numerically hard. However, computing points of F and H are easy. If you manage to find a point in S that is feasible, then you could be assured that T is infeasible. So that's it for this lecture. I hope you found it beneficial. We talked about weak alternatives. That is, our main interest is to find if set S is feasible. Sometimes it turns out to be hard to compute this numerically, and you'd want to reformulate your S set to another set that might be or might turn out to be easier. That is, in our case, set T, which is this set over here, lambda positive and G lambda nu positive as well. Well, doing a bit of math over here, that is, we formulated the problem, the optimization problem, that is to minimize 0 subject to S. We found its optimal value that tells us that is an indicator function, right? So P star is an indicator function. It tells us it returns 0 if S is feasible, else it returns infinity if S is infeasible, right? So we wrote down the dual function and the dual problem to arrive at D star, which is itself another indicator function. It's 0 if T is infeasible, else it's infinity if T is feasible. And using weak duality, we arrived at the weak alternatives that tells us that at most one of the two, T or S, is feasible. If T is feasible, then S is infeasible. Else, if S is feasible, then T is infeasible. This might turn out to be useful when working with inequality and equality constraints that are numerically hard to compute. So let's say your set over here is really complicated. Numerically, it might take a lot of time to figure out if this set has a candidate point that, satisfies the constraints and thus it's feasible. So you might want to take a look at T instead, which might turn out to be easier. Now, let's say you're in this situation and T is feasible. You found the lambda and nu such that T is feasible. And the motivation over here again is that this set is easier to compute numerically. So if you were able to find a lambda and nu that satisfies T, then you could be assured that there is no X that could satisfy S, and vice versa. Let's say computing G is numerically hard and F and H are easy. So if you find an X that satisfies S, then you could be assured that there is no lambda and nu that satisfy T, right? And all this discussion does not make any assumptions on Fi and Hi. We don't assume in any way that Fi's are convex and Hi's are affine, right? There's no assumption on that. The only assumption we make over here is that D, the set D over here, that is the domain of the problem, is non-empty. We don't care about an empty region, right? So that's it for this lecture. I hope you enjoyed it. Please leave a like on the video, subscribe to the channel. If you have any questions whatsoever, kindly leave a comment down in the comment section below, and I'll make sure I'll get to it as soon as possible. Also consider donating to my Patreon account any amount you wish. Thanks for watching, and I'll see you in future lectures.